In this episode, we're going to make security testing for AI systems feel concrete and approachable by anchoring it to three things you can always name, even as technology changes: the model, the data, and the use case. When beginners hear security testing, they often picture a generic checklist or a dramatic hacking attempt. But AI security testing works best when it is tailored to what your system actually does and what it can actually touch. A model that only summarizes public text has different risks than a model that can retrieve internal documents, and both are different from a model that can trigger actions in downstream systems. Testing that ignores those differences can waste effort while missing the real weak points. By the end, you should understand how to design a testing approach that matches your system's shape, why that match matters, and how to think about tests as a way to build confidence rather than as a way to hunt for perfection. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. AI security testing is the planned process of checking whether an AI system behaves safely under realistic conditions, including normal usage, accidental misuse, and deliberate abuse. The reason this matters is that AI systems can fail in ways that look acceptable on the surface, such as giving confident wrong answers, leaking sensitive context, or behaving inconsistently when prompts and data are slightly changed. Beginners sometimes assume that if a system works on happy path examples, it is safe enough, but security is often about what happens on unhappy paths that ordinary demos never show. A good testing design aims to reveal where boundaries are weak, where controls can be bypassed, and where the system's behavior becomes unpredictable in ways that create harm. Another important point is that testing is not only for attackers, it is also for your own team, because teams need to know where the system is brittle so they can design guardrails. When testing is tailored, it becomes a reliable source of truth about what the system can and cannot be trusted to do. The first pillar of matching your testing is understanding the model you are using, because model characteristics shape what kinds of failures are likely. Some models are used in a way that is mostly static, where inputs are simple and outputs are suggestions, while others are embedded in complex pipelines with retrieval, long context, and tool use. Some systems rely on a hosted vendor model, and others rely on an internally managed model, and those choices can influence what visibility and control you have. A model might be more likely to follow untrusted instructions, more likely to hallucinate, or more likely to reveal fragments of context depending on how it is prompted and constrained. The goal in testing is not to label a model as good or bad, but to discover its behavioral tendencies in your environment. Beginners should notice that you do not test a model in isolation. You test how your system uses the model, because the wrapper around the model often determines what the model sees and what the model is allowed to do. The second pillar is data, because an AI system's data is not just something you store, it is something you feed into the model's reasoning and outputs. Testing must reflect what data sources the system can access, how those sources are selected, and what sensitive content can enter the model context. A retrieval system might pull internal documents, customer records, or policy manuals, and the risk is not only whether those sources are secure, but whether the retrieval scope is too broad and whether sensitive details can leak into outputs. Data can also include user-supplied inputs like uploaded files or long conversations, which can introduce both accidental sensitive data and malicious instructions. Beginners often think of data risk as a storage problem, but in AI systems it is also a flow problem because data moves through prompts, logs, caches, and outputs. A good testing design includes checks that the system does not reveal what it should not reveal, that it does not overreach into unnecessary data, and that it handles untrusted content as content rather than as authority. Testing data pathways is how you discover hidden exposure before real users find it. The third pillar is the use case, because the same model and the same data can be low risk or high risk depending on how the output is used. A system that drafts internal text for human review has different consequences than a system that directly sends messages to customers, and both are different from a system that influences approvals, prioritization, or operational actions. Use case also includes audience, because a small trained internal group can tolerate more nuance than a public audience that will assume outputs are official and correct. Use case includes the tolerance for error, because some contexts can handle imperfect suggestions while others cannot handle confident mistakes. Beginners should take this seriously because security testing is partly about harm prevention, and harm depends on how outputs are applied. If outputs can trigger actions, testing must focus on action safety, validation, and containment of mistakes. If outputs are advisory, testing must focus on leakage, manipulation, and misleading authority. Use case matching keeps testing grounded in real consequence, which is the only way to prioritize tests sensibly. Once you understand model, data, and use case, you can design a testing strategy that covers the most important risk stories instead of chasing everything. A good starting approach is to translate risks into scenarios that can be tested, such as whether the system can be tricked into revealing restricted data, whether it can be manipulated by untrusted content, and whether it can be induced to produce unsafe or disallowed outputs. Another scenario is whether the system behaves predictably when context is missing or stale, because degraded context can produce misleading answers that users still trust. Another scenario is whether the system respects role boundaries, meaning it behaves differently for different users and does not let a low-privilege user reach high-privilege data or capabilities. Beginners sometimes treat testing as a search for any failure, but the more effective approach is to test for failures that matter in your environment. That means choosing scenarios that match your data sensitivity, your user population, and your downstream integration capabilities. The result is a testing plan that has purpose, not just activity. It also helps to align AI security testing with the software development lifecycle, SDLC, so testing becomes part of building, not an afterthought at the end. After the first mention, we will refer to this as SDLC. When testing is only done right before launch, teams feel pressure to ignore findings because deadlines are near and changes are expensive. When testing is done earlier, findings can influence design choices, such as narrowing retrieval scope, adding stronger policy checks, or redesigning how outputs are used. In AI systems, early testing can reveal that a feature should be split into safer modes, where low-risk behavior is enabled widely and high-risk behavior requires tighter controls. Beginners should see that SDLC alignment is not bureaucracy. It is the practical way to reduce cost and stress. If you bake testing into design, you discover risk boundaries while you still have flexibility. That flexibility is what makes your controls more effective and less painful. A core element of AI security testing is adversarial testing, which means you intentionally try to make the system misbehave using realistic abuse cases. This is not about being clever for its own sake. It is about simulating how a curious user or attacker might probe your boundaries. Adversarial testing can include attempts to bypass policy rules, attempts to extract sensitive data through careful questioning, and attempts to use untrusted content to inject instructions that override system intent. It can also include tests that try to cause the system to generate unsafe guidance, because harm can occur even without data theft. The key is that adversarial tests must be tied to your use case, because the same prompt can be harmless in one system and harmful in another. Beginners should also understand that adversarial testing is most valuable when it is repeatable, meaning you can run it again after changes and compare results. Repeatability turns adversarial testing into a measurement tool for improvement rather than a one-time stunt. Another essential testing category is boundary testing for data access, because AI systems often retrieve data or incorporate context in ways that users cannot see. Boundary testing asks whether the system retrieves only what it should, whether it can be coaxed into retrieving more, and whether sensitive fields can leak through summarization or paraphrase. For example, if the system is meant to answer using a limited set of documents, tests should try to push it outside that set by asking for related content or by using ambiguous prompts. If the system uses role-based retrieval, tests should verify that users with different roles truly see different scopes, and that lower roles cannot infer or extract higher role content. Boundary testing should also consider logs and storage, because sensitive data can leak into records that are accessible to too many people. Beginners should recognize that data boundary failures are among the most common high-impact AI risks because they create confidentiality exposure without requiring advanced exploitation. When you test boundaries intentionally, you reduce the chance that production users discover them first. Testing must also include resilience and degraded mode behavior, because safe systems do not only behave well when everything is perfect. A retrieval system might have partial outages, a vendor might return errors, or a data pipeline might deliver stale data, and the AI system must handle those conditions without producing misleading confidence. Resilience testing asks what the system does when context is missing, when a safety filter fails, or when an integration is unavailable. A dangerous failure pattern is when the system continues responding with high confidence, but without reliable context, because users may not notice the absence and may act on wrong information. A safer pattern is to restrict scope, refuse certain requests, or clearly guide users towards safer alternatives when the system is not trustworthy. Beginners should understand that resilience is part of security because incidents and outages create pressure for shortcuts, and shortcuts often create harm. Testing degraded behavior ahead of time helps teams choose safe fallbacks, not improvised ones. A meaningful testing design also includes output evaluation tied to policy and harm, because outputs are the visible surface where users experience risk. Output testing asks whether the system follows the rules it is supposed to follow, whether it refuses requests it should refuse, and whether it produces content that could cause harm in your context. For internal systems, this might include checking whether the system avoids exposing sensitive internal details and responses. For customer-facing systems, this might include checking whether the system avoids disallowed content, avoids misleading authority, and avoids instructions that could cause unsafe actions. Output evaluation also includes consistency, because inconsistent behavior can be exploited and can undermine user trust. Beginners should notice that output testing is not the same as quality testing, because security cares about boundaries and harm even when the answer is fluent. A fluent answer can still be a dangerous answer if it reveals data, misleads users, or triggers unsafe action. Testing should therefore include both policy compliance and safety impact, not just correctness. Because AI systems often change over time, security testing should be designed as a regression practice, meaning you rerun tests after changes to ensure you did not reintroduce old failures. Regression testing matters because fixes can be fragile, especially when they depend on prompt templates, filter rules, or vendor behavior that can shift. Beginners sometimes assume that once a vulnerability is fixed, it stays fixed, but in AI systems, small changes can reopen old gaps. A practical testing approach, therefore, maintains a set of known risky prompts, known boundary cases, and known failure scenarios that are rerun whenever models, prompts, data sources, or integrations change. This does not require endless effort if the test set is focused on your highest risks. Over time, the test set becomes an institutional memory of what the system struggled with and what controls were required to stabilize it. That memory prevents repeated mistakes and reduces the chance of drift toward unsafe behavior. Another important piece is deciding how to measure success in testing without demanding perfection that will never arrive. Security testing should produce findings that can be triaged, fixed, and tracked, and it should clarify residual risk, meaning what risk remains even after improvements. Residual risk, RR, is the remaining risk after controls and fixes, and after the first mention we will refer to this as RR. Beginners should understand that RR is not failure, it is reality, because all systems carry some risk. The value of testing is that it reduces RR and makes what remains visible and owned. Testing success can include fewer policy violations under adversarial prompts, fewer sensitive data leakage cases, improved refusal consistency, and safer behavior in degraded conditions. It can also include improved evidence capture for investigations, because testing often reveals gaps in logging and correlation. When success is defined clearly, testing becomes a tool for progress rather than an endless search for impossible safety. To keep testing aligned with the real world, you also need to consider who performs testing and how it is reviewed, because human perspective affects what you find. Some testing can be performed by developers and engineers during build cycles, and that is valuable because it catches issues early. Some testing benefits from a separate perspective, such as a security team or a red team, RT, that tries to break assumptions and explore edge cases, And after the first mention, we will refer to this as RT. Even when you do not have a formal RT, you can still adopt the mindset by assigning someone to play the role of boundary tester and misuse explorer. Reviews should focus on whether findings are understood, prioritized based on likelihood and impact, and translated into concrete control changes. Beginners should remember that testing output is only valuable if it leads to action and if action is verified through retesting. The loop of test, fix, retest is how confidence is built. Finally, testing design should include documentation and communication that makes results usable for decision makers, not just for technical teams. A good test report explains what was tested, what was found, what the likely impact could be, and what changes are recommended, using language that aligns with risk management rather than technical drama. It should also record which assumptions were validated, such as data boundaries and role restrictions, because those validations become part of your safety case for operating the system. For AI systems, documentation should also record any known limitations, such as areas where the model is inconsistent or where certain classes of prompts remain risky, because those limitations can inform user guidance and monitoring priorities. Beginners should see documentation as part of trust building, because it helps leaders approve use cases with awareness rather than with hope. It also helps future teams understand why certain controls exist, which prevents them from being removed during convenience-driven changes. Testing that is not documented tends to be forgotten, and forgotten lessons are how staleness returns. As we close, designing AI security testing that matches your model, data, and use case is about building a tailored system of checks that focuses on real exposure and real consequence, not on generic hype. The model shapes behavioral tendencies, the data shapes what can be leaked or manipulated, and the use case shapes the harm that outputs can cause and the level of control required. A strong testing design includes adversarial misuse exploration, data boundary validation, resilience and degraded mode checks, and policy-focused output evaluation, all aligned with the SDLC so issues are found while changes are still affordable. Repeatable regression tests keep fixes from drifting backward, while clear success measures make progress visible and defensible, even when RR remains. The right testing approach builds confidence because it replaces assumptions with evidence and makes controls measurable, which is exactly how AI risk can be managed while still enabling the business to move forward.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit BareMetalCyber.com.